class we are going to discuss something on wave packets. So, we are going to discuss something on wave packets. What is a wave packet? How do we define? And localized wave packets. Localized wave packets. Motion of a wave packet. Then the relationship between group velocity and phase velocity. Group velocity and phase velocity. So we define first what is a wave packet. So what is a wave packet? How it is defined, and what are the concepts for making a wave packet in quantum mechanics? We will describe first. Classically, suppose if we consider a particle, definitely we know the position of the particle and the momentum of the particle. Particle has a mass and this moves from one place to another place. Suppose for example, then definitely this will have a velocity and the position classically. So classically we will know the position and the velocity of the particle. So particle is well localized. Particle is well localized. So particle is localized in a space. Particle has different position and velocity, and we will know the position of a particle classically. So definitely particle will be there. So one can easily say that particle is localized. So well-defined space is localized. Well-defined space. Suppose if we consider a particle, for example, you chop, and I know the position. If I drop it, I know the momentum because velocity is there. And definitely this is well defined. So localized space. So particle is localized in a space classically. But quantum mechanically this is defined as particle is defined as a wave function. Wave function. So wave function psi is a function of r naught. So any particle is defined as a wave function. It is not a localized. So not localized in space. Not localized. Suppose if it is localized in space, then that's called wave packet. Suppose when localized in space, that's not wave packet. Okay, so wave function, which is a function of the position and time. Now, how a wave packet is can be obtained? How we can think of a wave packet in quantum mechanics? Suppose if we consider wavelengths, we consider a wave, and this will have a definite gamma. So wavelength is known. Wavelength is known. And what are the position of the particle? Position of the particle. Where the amplitude is high, is nothing where we can find out the positions. So amplitude is high somewhere here. So the property of finding a particle will be high enough to be here. And what are the position? It extends from minus infinity plus infinity. Minus infinity plus infinity. Correct? So position cannot be known. But lambda is known. Position cannot be known because this this extends from minus infinity to plus infinity. So particle can be anywhere. But lambda is not. Definitely lambda is not. This del x is uncertain. Del x is uncertainty in finding the position. So uncertainty is very large here. Of course, lambda is well known. So P equal to h by lambda. So the momentum of the particle is correct because lambda is well defined. The momentum of the particle is known according to de Broglie. So one is known, another one is not known. So del P is known, whereas del x we have uncertainty, large uncertainty in del x and definite value for del P. But instead of going for this wave, suppose we have wave of minus. And how to find out lambda? Lambda is ill-defined. Okay, yes. But definitely lambda will have some uncertainty. Definitely. Because lambda ill-defined. So lambda is ill-defined. What is the position? Position is known because somewhere here known. The position is known. So del x uncertainty is somewhat very less. Here del x is very large. Del x is very less. And del P also will be very small. Correct? Del P also will be very small. Uncertainty in momentum. Finding the particle's momentum is again this uncertainty is small. So wave pattern in which wave pattern in which del P also and del x also both will have less uncertainty. And here we have a lot of waves, they have constantly moving. So in a wave pattern, wavelengths of different wavelengths, waves of different lambda, different wavelengths, they will be constructed in different. And distinctly elsewhere, we said we will not have any interference. So distinctly elsewhere. So x cannot be found here. So less probability or zero probability of finding a particle somewhere there, other than this wave pattern. But probability of finding a particle, for example, probability of finding a particle where the amplitude is very high. So it will be somewhere here. So wave pattern in which del P, del x both will have less uncertainty. So that's why wave patterns are being selected for any quantum mechanics. Okay, so this is a definition for wave pattern. So wave pattern in which there is a larger probability of finding a particle, of course. So del x is known, del P also known, del x and del P both will have less uncertainties. So one can easily achieve this wave pattern. So wave pattern is a concept of any particle in quantum mechanics. This is also localized in space. Okay. Now, more localized wave particle. So we have elaborated in C, localized wave. As I said earlier, any wave function psi of rt, and this can be, say for example, in one dimension, this can be written as 1 by 2 by minus infinity plus infinity, say pi of t e power I k r minus omega t into d. So any wave function, okay, which is a function of x comma t. So particle moves in one d. Particle moves in 1D. amplitude of the wave. Amplitude of the wave. Suppose at t equal to 0, say particle is at t equal to 0, then this can be known as psi of x, which is equal to psi so we have 1 minus 5 minus plus infinity pi of t e power I. So here is something x because what is the case charge. So we have e power I kx dt. At x tends to 0. Consider as x tends to 0. At x tends to 0, e power I kx e power I kx becomes 1. It is well localized. See? It is well localized. At x tends to 0, it means particle can be formed somewhere here. So e power I kx becomes 1. So e power I kx becomes 1. So particle can be definitely formed somewhere here in the space. And now phi of k is nothing but area phi of k is amplitude of the wave is this is the Fourier transform of this is in k space. So Fourier transform. Transform of psi of x. So for example, we have this psi of x and x. Okay, where phi of x will be Fourier transform of this. That will give you it's a Gaussian wave. Fourier transform of the Gaussian wave. So at x tends to 0, e power I kx becomes 1. So definitely particle can be formed somewhere. Okay. So psi naught of x. This is the wave function is there. So probability of finding a particle is nothing but O psi of x. Okay, psi of x. Suppose we consider psi of x whole square. Okay, the square of psi of x. This is nothing but probability density. First one is probability of finding a particle. This is probability density. Probability of finding a particle between one region to another region. For example, probability density. Probability of finding a particle between x and x plus x. Then this becomes we have phi of k and we are going to take the mod square of this one. So e power I kx multiplied by e power minus I kx. So that will get cancelled. Okay. So you will get only phi of k. This is in k space, and of course we know only p equal to h bar, right? We know only p h bar. This is in k space, so this is in momentum space. If I replace k equal to p by h bar, this can be represented in momentum space. So x, the Fourier transform of x is nothing but momentum space. So space, Fourier transform of space, that will give you momentum space. Real space into momentum space. Okay. So now probability of finding a particle. This is the probability density. So probability of finding a particle exactly equal to the amplitude, the square of the amplitude of the particle. So a particle is well localized. A particle is well localized. A particle is well localized. One can easily find out the wave function, probability of finding a particle, which is nothing but in the highest probability. So this is the highest probability. Okay? Highest probability. Suppose we consider that this is the highest probability of finding a particle. So phi of k is the amplitude. So phi of k is the amplitude, it means the probability of finding a particle somewhere here. So highest probability phi of k is the amplitude square. So somewhere here amplitude square is nothing but intensity. Suppose phi of, see here one can say that probability of finding a particle, that is probability density of probability density, square is probability density. So probability density is exactly equal to the square of the amplitude of any wave for any localized wave. Suppose particle is in motion. So we have to consider this particle is in motion. Motion of a wave. Then of course use this equation. Take off beta phi of x comma t is equal to 1.25 minus infinity plus infinity. We have phi of k e power I k x minus omega t into d. Here we are going to consider this omega is a function of omega. So we have large number of waves. Omega is a function of k. It means large number of waves. For example, you have wave packet lengths. You have a wave packet as activated drawn like this. So wave packet. Actually, wave packet consists of lot of waves. Okay, with different lambda. So this wave packet consists of lot of waves with a different wave. Okay, different lambda and different phase, of course. Different lambda, different phase, they interfere constructively. They should interfere constructively. And elsewhere we can have only destructive effects. Only that this wave packet will exist. Okay? Because definitely del x and del b will have less uncertainties. They have less uncertainties in the wave packet. Particle will be somewhere here. And particles surely will have momentum because lambda can be known. X is also defined and p is also defined. But uncertainty is very less. In this case, x cannot be defined. Particle can be anywhere between minus infinity plus infinity, somewhere here. But in this case, definitely particle somewhere, it will be somewhere here. But highest probability of finding a particle is highest amplitude. Okay. So we are going to consider now omega in terms of omega of k. So different waves we are going to consider. This is called dispersive medium. In a dispersive medium, lot of waves will have different waves. With phase. Different wavelength and phase. So now, how this can be done? Now, this equation can be done already by minus infinity plus infinity phi of k e power I just pull k out, that will give me x minus omega of k divided by k into t. I have taken this k out, so that will give me I k x minus omega of k divided by k. This omega of k divided by k is nothing but velocity of the into d. So omega of k divided by k, that will give me v. So this can return us 125 minus infinity plus infinity phi of k e power I k V naught okay. So now this can be written as totally this can be written as sin naught of x minus v naught. Okay. So now particle moves with the velocity v naught in the right hand direction. In the right direction. It means it implies that particle moves in the right direction. In the right direction. In the right direction. With the velocity v. Okay, because we have considered this omega. Omega is a function of frequency. Omega is a function of frequency. The lot of waves we are going to connect with different lambda. So now this phi of k becomes phi of k versus k. This becomes like this. For the highest amplitude we say k naught, for example. Then this phi of k becomes say some other function k minus k naught. If k naught is the origin, for example k naught equal to 0, then phi of k is equal to 0. Okay, it shifts somewhere from the origin. Okay, and this del k shift, del k becomes k minus k. Then this omega of k can be expanded. Omega of k can be expanded in power series. Expanded in power series. Okay. So omega of k which is equal to omega of k naught plus d omega by dk at k equal to k naught and del and goes on. So omega of k, omega depends on the wave number. So omega depends on because omega consists of many waves with different lambda and phi, and this can be expanded in terms of power series like this. So for time being, this one I refer as omega 1 plus d omega by dk. I define this as group velocity. Okay, dg equal to d omega by dk. This earlier we referred this v naught, which is defined as a phase velocity, which is equal to omega by dk. So this is a phase velocity. Suppose we take the wave packet. This is for group velocity. The velocity of wave will be your dt. Velocity of the wave dt is velocity, phase velocity. Velocity of wave is defined as dt. Velocity of the wave, phase velocity, and totally this is called as a group velocity. Group velocity is the velocity of the wave packet. Phase velocity is the velocity of the individual wave inside. Okay. So this can as d omega by d psi of x comma t can be done as 1 by 25 minus x plus infinity g of a minus k naught, correct? Phi of k can be done as g of a minus k naught e power phi k. Instead of k I can write this as k minus k naught x. Okay. K minus k naught x minus omega can be written as omega naught plus dg k minus k naught into t, correct? Then of course so all k naught is a constant one because we are going to integrate only with respect to k. So you pull all k's inside as integrals. All k naught should be taken outside. So this becomes 1 by 25. Okay. E power minus I k naught x. Then I get this out. And of course minus e power minus I omega naught into t, correct? So this must be I omega naught into t. Then another thing will be minus dg into, so minus minus plus that will be I into dg k naught t. So now the problem goes a minus k naught, g of a minus k naught. The remaining term e power I kx, right? I kx, I kx, then I kx, correct? Next one will be minus dg k. So this can be done as 1 by 2 pi e power minus I k naught x, I can pull k naught out, right? X minus dg t, correct? Into e power minus I omega naught t. Integration minus infinity plus infinity g of a minus k naught e power, I can pull again k out x minus dg into t. So now this represents a harmonic. This represents a harmonic. And whole thing represents an amplitude. This is a wave function, and this must be an amplitude. For any wave function, we have wave as well as an exponential part as well as we have amplitude part. So this represents an amplitude. So it's a harmonic, and this is represented by g of k minus g, the function of k minus k naught e power I k x minus b g t into dt. So this represents the group velocity. So this represents a group velocity. So I can write this as psi of x comma t, which is equal to again psi of x minus, as I have written, x minus b t. Okay. I can take the modulus on both sides. Psi of x comma t, which is equal to Again it implies psi of x comma t, the probability density of a particle finding between any region x and dx exactly equal to group velocity, where the particle is found maximum. The particle moves with velocity group velocity. Particle moves with velocity vg in a right direction. So this is exactly equal. So definitely particle can be found here and it moves with velocity group velocity. That's right. So motion of a packet can be thought of as a wave packet. Definitely particle will be there in the particular region in a wave packet. The highest probability of finding a particle will be in the peak, and particle moves with group velocity vg in a right direction. So both are equal. See? Now we go with the concept of the relationship between group velocity and phase velocity. And of course, we have defined the phase velocity. The phase velocity we have defined as dv equal to omega by t, right? And group velocity we have defined as vg equal to d omega by t. And omega equal to dp into k. So omega equal to dp into k. So therefore, I can differentiate d omega with respect to k. That will give me d omega by dk, which is equal to k into dvt by dk plus
dv into
dp. We know already k equal to 2 pi by lambda. We know already k equal to 2 pi by lambda. I take this term, say dvt by dk, which is equal to dvt by d lambda. I can write this as d lambda by, correct? So this can be written as dvt by d lambda. This can be written as lambda equal to 2 pi by k. So d lambda by dk equal to minus 2 pi by k square minus 2 pi by k square. So this can be written as minus 2 pi by. I take this k, 1k this side. So k into dvt by dk, that will give me minus 2 pi by k, correct? dvt by
d lambda.
instead of k I can write 2 pi by lambda. So that will give me 2 pi. Instead of k I can write 2 pi by lambda. So 2 pi by 2 pi lambda dvt by d lambda. So this can be written as k into dvt by dk can be written as minus lambda into dvt by. I can substitute it. So this becomes dv minus lambda dvt by.
d lambda.
So it implies this is nothing but your vg, correct? d omega by dk is nothing but your group velocity, definition of group velocity. So vg equal to dv minus lambda dvt by d lambda. It implies
Group velocity.
group velocity is lesser than of phase velocity. Group velocity is less than the phase velocity. Suppose that when you go for any indispersible medium, in which all the rays are definite vehicles, constant waves, same wave. Then dvt by d lambda equal to 0 because this is constant. It just becomes 0. So Vg equal to Vg equal to Vp because dV by d lambda equal to 0. Vg equal to so we know that P equal to h bar. Yesterday we said the relationship between momentum P and P equal to